XOR-based test compression is widely used in our industry to dramatically reduce test time and cost with only a minimal impact on chip size and power. Compression reduces test time by partitioning registers in a design into more scan chains than there are scan pins. As the compression ratio between the number of scan chains and the number of scan pins increases, the length of each scan chain decreases, which means fewer clock cycles for each test pattern and therefore a reduction in test time for each test pattern.
So what limits compression ratios from increasing indefinitely? Fewer clock cycles per pattern also means fewer bits of information in each pattern to control register values and detect faults. At some point, if the compression ratio becomes too high, the achievable fault coverage drops. Also, as the compression ratio increases, even if fault coverage can be maintained, the number of patterns required to maintain this coverage rises rapidly, since it becomes more difficult to pack the detection of multiple faults into a single pattern. As a result, there is a diminishing benefit on total test time from increasing the compression ratio.
In addition to coverage drop and pattern count growth, increasing the compression ratio also has a significant impact on the physical implementation of a chip, since every scan chain must be connected to and from the compressor and decompressor. When we profile the physical impact of compression logic across a range of customer designs at a typical industry compression ratio of 100x, it is already 4% of total chip routing resource. If we increase the compression ratio to 400x, then the impact increased to a staggering 10%, which would surely require a significant increase in die size to accommodate, and ultimately outweigh any potential cost savings from the reduced test time.
Our new Modus test solution introduces two major innovations backed by an extensive portfolio of over 10 patent applications to address the fundamental challenges of rising compression ratio: 2D compression and elastic compression. Elastic compression mitigates the fault coverage drop and pattern count increase challenges of high compression ratios. It can reach a 400x compression ratio without any impact on fault coverage and with an overall reduction in total test time of up to 3x. Elastic compression differs from traditional XOR compression by leveraging registers and sequential feedback loops alongside traditional XOR logic in the decompressor circuit. The sequential nature of an elastic decompressor enables a Modus automatic test pattern generation algorithms to leverage multiple shift cycles to control register values in a single fault capture cycle. Conceptually, this is like being able to borrow scan pins from previous clock cycles to help detect more challenging faults in the current clock cycle. An elastic decompressor can also adaptively increase the number of shift cycles in a test pattern to be larger than the scan chain length to provide yet more controllability to detect tough faults.
So 2D compression pairs with elastic compression by targeting the impact of high compression ratios on chip routing resource. The key insight between 2D compression is to leverage the entire two-dimensional nature of the physical chip layout to build an XOR network which can unfold into a grid structure across the chip. This 2D grid structure consumes 2x less routing resource than the traditional one-dimensional XOR compression circuits at a 100x compression ratio. Furthermore, the 2D compression structure scales sublinearly with compression ratios, and at a 400x compression ratio is still no worse for routing resource than traditional 1D XOR compression is at only 100x.
Cost of test directly impacts our customers' profitability, and our new 2D elastic compression technologies offer up to a 3x reduction in scan test time without any impact on fault coverage or chip routing resource.